Okay, let's do another proof that a language is non-regular. Here, a language L is the set of all binary strings that contain twice as many zeros as ones. And here it's not immediately clear what I'm going to choose as my string to obtain a contradiction, because here the zeros and ones could be in any order. So a good tactic for these sort of questions is to choose a subset of the language, choose some infinite class of strings, such that they're all in the language, and then you can like hot swap out part of the string using pigeonhole principle to obtain a contradiction. So what sort of strings in this language? Well, a whole bunch of them, but clearly these strings, epsilon, 1 00, 2 1s and 4 zeros, etc. Clearly all of these strings are going to be in the language, right? So I'm going to let the set, I'll call it G. It's going to be the set of all strings of the form 1 to the n, 0 to the 2n, where n is greater than or equal to 0. Clearly, G is going to be a subset of L. That is to say, every single string in G is in this language here, right? Because clearly each string has got twice as many zeros as ones. And so now we can do the same sort of trick as before. What we're going to do is we want to try to like pump up the ones using pigeonhole principle and obtain the contradiction. So we're going to assume that L is regular for contradiction. So there exists some DFA, we'll call it A, such that the language of A is going to be the same as this set squiggly L. So the language of A is squiggly L. Okay? So we're going to note that the set of all strings containing only ones is an infinite set. So we can pull the same trick as before. So therefore, by pigeonhole principle, from the starting state, if I read there's at least two strings in this set that end up in the same place, right? So by pigeonhole principle, there exists some I, there exists some j. I is not j, but from the starting state, if I read I many ones, end up at the same place as reading j many ones. So like intuitively, the DFA kind of forgets how many i's it's seen. It can't tell the difference between a string of I many ones and a string of j many ones, because it forgets, right? Because it's got finite memory. Okay. Clearly, all strings little g in this set G are accepted by A. Why is that? Well, A, the language of A is this set here, and every string in G is a subset of, is in this set here, right? Because G is a subset of L. So I'm going to pick N to be equal to I, and that way we can sort of get the same contradictions before. So we're going to let W be equal to 1 to the I, 0 to the 2I, which is a member of G. So that means from the starting state, if I read W, I end up in a final state. Substituting in the definition for W, we have I many ones and 2I many zeros. I can now apply append theorem and split this up, just like I did last time. And the sneaky trick comes in now. We're going to replace this term here with this term here. And we know they're the same state because pigeonhole principle told me so. 1 to the j, 0 to the 2i. It's still a member of f. And then you punch append theorem backwards. 1 to the j, 0 to the 2i. Is an element of f. So 1 to the j, 0 to the 2i. If this set here is a member of f, that means this string here is accepted by A. What sort of things does A accept? A accepts any string with twice as many zeros as ones. For this string here to have twice as many zeros as ones, it must be the case that it must be the case that I is equal to j, right? Because if we want this thing to have twice as many zeros as ones, 2 to the I has got to be exactly twice as big as j. That is to say, 2 to the I must be equal to 2 times j. Therefore, I equals j. Uh-oh, contradiction, same as before. We made a bogus assumption. Where is it? Here it is. Therefore, L is not regular. There we go.